Hi everyone, my name's Darron Thornbury. I'm from a company called Dazatronyx in Australia and I build guitar pedals. I'm making this video for my friend June, who's in South Korea, and he wants to build one of my Fetish Buffers. I thought it'd be a good starter project because he hasn't had much experience or any experience with guitar pedals, building them, but he's got a background in electronics and he's a clever guy. So I thought this would be the easiest one for him of all my pedals because the wiring's very minimal. There's in, out, positive, negative, and that's it because it's all mounted on the foot switch. So there's no extra wires for the bypass. There's no wires for pots or controls. So it should be pretty easy. I've got over here. It's going to look something like this. I've got the circuit boards. Here's the circuit board I'm about to drill for you, June. And the switch is going to mount to it. It's all going to mount straight on. Very simple. So I've made you up this cheat sheet. It's got the circuit board layout. So that should pretty much match. And I'll put the schematic up here. I've just drawn this. It's actually really simple. A buffer is very simple. It's a lot more complicated than it needs to be here, but there's extra little niceties and things that aren't necessary but a good practice. Some extra filtering. But you can see the board is still ridiculously small by the time you assemble it. This one's not quite done, but so I thought, yeah, I'll just go through it. And as I go through it, I can probably just talk off on different topics and cover a whole lot of stuff that's going to help you start building your first guitar pedals and continue to build some more afterwards. You know, when you start, you don't know what everything's doing, and you probably won't for a little while, and you build them, and then later on you'll see why that was the way it was. So anyway, I thought I'd just go through the schematic quickly. Signal will come in, through, and a signal will come out. And the job that this JFET's doing is sort of looking, air quotation, looking at the signal, using the 9-volt source, and copying the signal for a stronger signal is a way of putting it. It's going to have a very low output impedance copy of the original signal. So signal will come in. Almost every single guitar pedal or every audio circuit has an input capacitor and an output capacitor. Now what that's doing, the incoming signal is AC, as in it oscillates up and down like your guitar string. It's not DC like a battery. It's not a fixed voltage. It fluctuates, positive, negative. That will pass through. On this side, there is DC voltage, and that will not be able to pass through the capacitor because you can see the capacitor is made of two parts and they do not touch, so it won't conduct the positive electricity because at no point does it actually touch. But AC has a way of jumping across, I suppose is a nice way of putting it, and you'll see the signal on each side. Now because we're using true bypass foot switches, let's get one of those ready. Here's one here. So this is completely candid, so my office is in complete mess. Everything's lying around, but that's as usual for me, and yeah. So I'm not going to clean up, but yeah, it's not too bad. I've got everything sort of where I need it. So these are the true bypass foot switches. Hopefully you know what that is. That's the whole discussion. So the important thing to note, you learn this, it's one of the first things you learn with the coupling capacitors in and out. There's a 1 meg resistor here. And the job of that is to stop the capacitor and the switch from making a pop noise. So this is a mechanical switch. It'll physically disconnect the whole circuit, reroute as if a wire bypassed the whole thing from the input jack to the output jack. The reason you need this switch, remember I said there was DC on this side. There is voltage other than the guitar signal. And I did say that these two do not touch, so it can't jump across. But anything has a small, tiny amount of resistance. Even air, that's lightning jumps air, makes plasma. So if you leave that voltage there will slowly, almost immeasurably be able to leak onto the output. But if there's no load there, even the slightest bit of voltage will sit on this wire, and then when you hit the switch, it connects and the little bit of voltage comes through and it's heard as a pop, so you get the pop. If you ever have a switch going pop, 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 really loud, like a thud when you switch it, then I usually check to see if there's any DC. Maybe there's a leaking capacitor or a short across the capacitor. But that is a common cause for why your switch might pop. It's a really loud thud or just a tiny one. So this is a 1 mega ohm resistor, very large value resistor, 1 million ohms. So it's strong enough that it really shouldn't affect your signal. In theory, if you stack enough of them up, but 1 million ohms, no matter what your pickup, your buffer, anything should be able to handle that without even barely seeing it. But it's small enough that it will discharge that capacitor, it won't pop. That 1 meg resistor can be any value from realistically 500k up to 10 meg, 22 meg, because the resistance across this capacitor should be almost immeasurable, unmeasurable. With a regular multimeter, I've got my I've only got some crappy ones here. That's my mains, sort of rough AC one. This is a little tiny cheapy, but these are good actually. Tolerance on this is very good. Resistance, capacitance. You don't really need an expensive meter in the slightest. As long as it does capacitance, that's a good one, because sometimes the cheap ones won't, because it's a little bit more work to measure capacitors. Resistance and DC voltage are what you need. And when you pay for a more expensive meter, this one costs significantly more, but that's for field work. It's got a clamp meter, which you wouldn't use. It's for measuring high voltage AC. Even the cheap ones always get an auto range one. See, it just says ohms. You don't have to set 10, what sort of range you want. Low ohms, 10k, 100 ohms. It'll do that, and it'll measure DC. It'll set the range automatically, AC, anything low voltage up to mains. I've sidetracked myself, but yeah, I'm going to talk lots just on building guitar pedals, and hopefully this might even help some other people. Where was I? So yeah, the resistance across this capacitor should not be measurable if it's way above, maybe above 100 mega ohms, especially because this is a non-polarized capacitor. When you get into electrolytics and stuff like that, then you do start to get a little bit more leakage, or considerably more leakage, but still not very easily measurable, readable. And the reason is, I'll show you, this is a 10 microfarad capacitor. Or an even better example, this is a 100 microfarad capacitor. They're the same size, same package, they're usually around the same cost too. So, and this is a 1 microfarad capacitor. Now I can see physically they're about the same size. Has 100 times as much capacitance. These ones have a much thicker dielectric in that they are isolated much better on each side. They're the ones that are good for audio. Not that it really matters, but if you have a choice, I always use a non-polarized cap first, and then failing that, electrolytic Yeah, just size practicalities, really. That's why you use electrolytics and polarized capacitors. They're much, much smaller. Say you needed 100 microfarad non-polarized, that might be, you know, bigger than the whole circuit board. So anyway, keep going, keep going. So signal comes in, comes through this capacitor, and I'm going to detour, sidetrack a lot. Now the value of this capacitor is important. This one not so much, but in all circuits. This circuit, I want a full frequency response. I don't want to change anything. Bass, lows, I want the input to sound exactly like the output, no matter what instrument you plug in. Bass guitar, guitar, violin, keyboard. Now I've selected 1 microfarad for the input, and the smaller the capacitor, the less bass that's going to pass. Depending. Now 1 microfarad will pass everything. 1 microfarad should pass everything here. Here you could have used even 100 nanofarad, which is 0.1 microfarad, a tenth of this value, but because I have the capacitors here, I just chuck them in, and, you know, why not? What's going to influence this though, what changes the frequency, isn't just the capacitor size, it's how much resistance you have after it going to earth. And those two form an RF filter. In this case, there will be a high pass filter because it determines how high the frequencies are that pass. And I want very low frequencies like 100 hertz, 50 hertz even. Why not? Anyway, moving on. So it's passed through, all the bases pass through. It'll run through this 220 ohm resistor, 220 ohms. That's 0.22 kilo ohm. This is a very, very, very small value in terms of audio circuits anyway, low voltage audio circuits. A lot of circuits, overdrives and stuff especially, might have anything around 1K at the input, and usually all it's doing is protecting the FET or the transistor from damage. Say somebody put the circuit in a powered and active amplifier loop. That's a much, much heavier voltage. It's usually about 10 times as hot in voltage as a passive guitar signal, because a passive signal off a guitar is incredibly weak. It's a flimsy little whisper in terms of electronics. I've selected 220 ohm though, which is much smaller. You could leave it out, but it is there for a little bit of protection, just tiny spikes. And I've used a small value because I really don't want anything to affect the buffer. The buffer should be transparent. You should be able to stack 10 of them without, you know, throughout the pedal board without too much alteration. There's always a tiny bit though. Every time you run a buffer, no matter how ideal you make the circuit. That's why mine has a foot switch too. You can really sit there in A, B, and you should not hear anything, but with a keen ear you will hear a tiny, tiny bit of difference. Okay, keep going. And there's a capacitor ground. For that I use just a tiny ceramic capacitor, which I'll grab here. Something like this. Then these ceramic capacitors are the ones that you have to use for very, very low values. And all that's doing is rolling off the extremely high frequencies, and in this case the frequencies that are above the guitar and even the human audible range. Again, that's not necessary either, that's just good practice. And if you talk to the old amplifier guys, anytime, no matter what sort of amplifier it is, even non-audio, one of the good practices is to remove any frequencies that you aren't actually dealing with, because they can create different problems, even though they're out of the audio range. Okay, keep going. So it's come through. The FET has an output. This 10K helps it bias. It can be anything from around 3.3K up to 10K. Lower probably would be better here, but I'm using a 10. Through the 1 mic cap and out. Now the value of the 1 microfarad capacitor again, isn't critical. 1 mic is the minimum I would use. You could probably use 100 nano, 0.1 microfarad, and it wouldn't make a difference, but it depends on what sort of load you've got afterwards, what you'll plug it into. You have no idea what this buffer is going to plug into, an amplifier, a crappy pedal, some weird setup. And the idea of this circuit is to make the signal as ideal as possible. Now, you could use an electrolytic large value, like an extremely large value, 22 microfarad, 10 microfarad, or you can use both. You can use them in parallel with each other. But I've used just that one non-polarized cap because I have literally 1,000 of them, and I prefer it over an electrolytic. So we haven't talked about this whole top half here. Positive voltage will come in. I've written 9 to 18. It can even go higher, but they're the standard voltages people have. And it will automatically rebias if you increase the voltage. A higher voltage will give you more headroom, so you can run a hotter signal, less likely it's going to clip. I like the idea of using a single FET. It even won't be as low noise. An op-amp, an actual chip, even though it's got heaps and heaps of transistors, heaps and heaps of parts, they've made an ideal circuit that will keep it sterile, exacting, very, very, very low distortion figures. This won't distort. It'll be very, very linear, but I just like this idea more like the tube days. You've got one device. If you do clip it or anything, it's going to compress nicely anyway. So positive voltage comes through the diode, the protection diode, just in case polarity's backwards. They've hooked it up to AC or something accidentally. Hopefully this would even survive AC without any problems. It'll definitely survive a reverse battery. Then I've used 47 ohm immediately afterwards. So the whole circuit comes through this, and all that does is regulates the voltage down a bit. It's not a fixed regulation. It's very rough, but it's much better than nothing. Following that, I've got an enormous 220 microfarad capacitor. It filters the power for the whole circuit. So any little bits of ripple noise, hopefully that should take out a lot of it. 220 is very, very large. Normally on a schematic you'd see it'd be about 100, but I really just wanted to overkill for some reason when I did this. And sometimes there's another one. This is a polarized cap. Sometimes there'll be a non-polarized cap too, because the polarized ones are better for lower frequencies. But because of their structure, a non-polarized one will handle all the higher radio frequencies and stuff, get rid of them a bit better. Now, it's extremely common that circuits have a little filter capacitor, and every circuit should. It's not necessary, and you probably won't even hear the difference, but it's very good practice just to stop problems with them talking to each other and noise back and forth. But a lot of the time people eliminate this little resistor, and without that resistor, this capacitor actually doesn't do anywhere near as much. It's magnitudes more filtering happening if you put in that tiny resistor. You'll shave off a little bit of voltage depending on how much current you're drawing. So if you've got a high current circuit, you'll need a lower value resistor. This is drawing almost nothing. So it's going to drop out a tiny bit of power, and I can use a large value, 47. Normally they might be like 10 ohms, which is extremely small, but you don't want to mess with the voltage much. Anyway, moving on. Now there's a point where, so that's powering the FET, and there's a point where there's DC power coming here to bias the circuit. Because we don't have a split rail supply, it's not a positive negative supply, it's just 9 volts positive and 0 earth negative. You have to put the AC signal sort of in reference to your positive voltage between positive voltage and earth. And to do that, we're putting half of the incoming voltage onto the AC audio signal, the guitar signal. Half is sort of a good guess. It might have been better, a little bit higher, a little bit lower. So the way that that's happening, 9 volt will come through here, roughly. And between this 10K and this 10K, between two equal loads, you'll always get half the voltage. So that should be about 4.5 volts, because these two resistors are battling it out down to earth. So that's like a 20K load. In the middle of the 20K load will be 4.5 volts. And there's another little tiny filter cap which will just stabilize and get rid of any noise, because even resistors, I mean, metal film resistors, everything, every time you make a transaction with voltage, there's a little bit of noise because of the physical properties of the material the voltage is passing through. Again, without that cap, you probably wouldn't notice a thing. It would be the same, but good practice. Let's do everything the best. Why wouldn't you do everything the best way you can? Now this DC will connect to the AC through another 1 meg resistor. That's a very, very high value resistor. And that resistor could be anything 10K up to 22 meg probably. It wouldn't make a difference. But in theory, that's a good value because it's high enough not to affect the signal too much. Not that it should. The higher the value you go, though, higher value means you're passing through more material and in theory injecting more noise. But again, I wanted this buffer to not drop out volume and to be ultra clear. And noise definitely isn't a problem. This is a discrete circuit. It's very, very, very low noise. Now, the DC bias should always come before this little protection resistor. It doesn't matter much, but in theory, because if you moved it and after here and you had a 1 meg, then these two would form a voltage divider and you'd shave off a tiny bit of your AC voltage. Not much, 220 ohm versus 1 meg is negligible, inaudible, but again, it's just good theory. Oh, and these two, I've just put a couple little Zener diodes here. Originally, there's no 1 meg resistor because of the way I'm wiring the switch. It probably won't need it, or it doesn't. I used to use a 1 meg here, but now I've got a couple little protection diodes, and they're back to back or front to front, whichever way. It doesn't matter how you wire them as long as they're facing in opposing directions. And they're going to, hopefully, it's just in theory, protect the FET if there's ever some little spikes over voltage. FETs are incredibly vulnerable compared to regular bipolar transistors. One reason manufacturers don't use them, they're a pain to work with, but they're sort of nice too. That probably would have been better if that was connecting on the other side of the cap, but the layout just accommodated that. So yeah, I've been talking for 24 minutes. My God. This will be the layout. You can see it's all kind of correspond, but this way you can match them up. And let's get into it. Hey, now's probably a good time to discuss tools. Definitely need a soldering iron. This is a nice regulated 100 watt iron, so you can see it turn on and the temperature will come to a fixed value. I've got that set at 360-ish at the moment. Depends what you're doing. And so you definitely need an iron. You don't need a regulated one. You can buy a cheap one, and for pedal work it really isn't going to matter too much. It won't be like mine. You probably have to leave it there for about 5 minutes for the temperature to sort of stabilize. It won't be incredibly accurate, but you know, as long as you do a good job, it doesn't matter. Definitely need some side cutters. These are some nice ones. They're not high tensile, just very delicate for cutting wires and leads and stuff. You don't need this, but I also usually keep some crappy ones for doing rough snaps and stuff like that. Probably a shifter will do everything. You don't need spanners, sockets and stuff. If that's all you've got, 6-inch, that's all you need. Does everything. A pair of pliers would be nice. These are flat needle nose. See, there's no grip or corrugation. I don't know what that's called. So these are definitely good. I've also got some pliers that, again, they're cheap, but they're really rough that you can use for gripping stuff. But if you can get some without, they're just flat, that would be fantastic for electronics. And I think that's about all you'll need. Like, you shouldn't have to invest in much. I've got this solder sucker here. If you make mistakes, it would be really good to have one of these, but you'll find that out. Otherwise, you can buy soldering braid, desoldering braid rather, which I'm not very good with. There are some aluminium metal ones that are smaller than this, and they're the cheaper ones, the more common ones. They work. I really don't like them, especially compared to this. This is branded Goot solder sucker, made in Japan, and I believe I bought this from Rockby Electronics in Australia, and all that. Hopefully we won't need to make any mistakes or suck them up today or desolder or anything, but it pressurizes with a spring, and then you liquefy the solder, it sucks it up inside and eject it out. And yes, sorry, you definitely need solder. There's a few different types. This must be discussed. I use a lead-free solder. Solder. That's correctly pronounced solder, but in Australia we call it solder. Different sizes. It doesn't really matter what size you get. 1 mil, 0.8 mil. I think this is 0.8 or 0.5, 0.8. It's fairly fine, but it really doesn't matter. Depending on your country, leaded or unleaded might not be available. Traditionally, everybody used leaded solder, but due to ROHS restrictions, they're trying to phase that out. And a lot of countries, it's mandatory. Australia, not yet. America, not yet. Europe and Japan, Asian countries, it is. They're enforcing it. And the idea is to stop lead going in landfill, stuff like that. Things are going in landfill, the chemicals are going where they're not meant to go. It's bad for the ecosystem, human health, etc., etc. I use an unleaded one, so it's majoritively tin. People complain, say it's harder to work with. If you use a good iron, I disagree. I think it's actually better in a lot of ways. You just need to turn the iron temperature up. But if you're a beginner, I suppose they always suggest that you start with leaded, which is 60-40, 60% lead, 40% tin. Solder, because it's magnitudes cheaper. Say this roll cost me $100 or so for it's a kilo. A leaded one might have been $15, and a kilo of solder will last you, if you're an amateur, years and years and years, like 10 years. You don't need that much. You probably just need like this tiny little tube or 100 grams or something, But yeah, it's heaps cheaper for lead. Depends if you're environmentally conscious. And you'll need wire, obviously. I've got different wires and varieties. Whatever you like, the gauge doesn't really matter. I'm using here 22, 24 gauge wire. It's mostly just what you like to use with your fingers. It's not going to influence the sound or anything. Yeah, nice work lamp. You don't need extraction fans or anything like I've got here. I'm about to drill these circuit boards. I've acid etched them, cut them down, and I've just brushed them and tinned them. So you see it's not like a copper color anymore, it's a silver metal color. That's there to help. If it was just plain copper, it'll oxidize, which is like rusting pretty quick, like a couple of weeks sort of, you get to play with it. And once I've started using it, you're not going to be able to brush it and clean it very easily. Usually you get a spray, protectant, an aerosol spray, and that'll put a film in between the air and stop it from having any problems, but it's sort of messy to solder with. Nobody does this. This is above and beyond. People don't tin their circuit boards like I do. But anyway, I'm sending this to you, June. It'll be easiest to work with it within the next sort of couple of weeks. If you let it sit there for 6 months, it'll probably be harder to work with, but it'll still work. And to drill, a lot of people have done this. I bought this years and years ago. It's a Dremel, like a plain Dremel tool in a Dremel branded plunger. I regret buying this. It's fantastic and it works really well. It's plastic. It's not super rigid. The only thing I really don't like about it is that because I've now got this Dremel tool suspended in here, it's just a bit of a pain in the butt to get out and try and repurpose this tool to do anything again. So this Dremel has become a dedicated drill press now, and it defeats the purpose. So really, I really would have rather just buying a small drill press to dedicate to being a drill press, not this workaround adapted thing. But it's because it's got this tiny little plunge that only goes this tiny distance. It's perfect for PCB, so I haven't replaced it. If it dies, I won't buy another one of these, and it shouldn't die. The other thing is too, all the Dremel gear is very, very overpriced, expensive. This would be great if you lived in Europe or you were sharing a tiny little flat, you didn't have the space, you could repurpose this into doing other jobs, but for production reasons, I really can't be bothered taking this out, in and out, in and out. I've even actually bought further Dremels, like I've got a little line on low voltage one. Failing that, I just use a drill. The drill press is outside for drilling the boxes. Another day, it's night time now. Hi, it's me. Yep, okay. Oh, that's what I want to show you. This is the drill bit I'm using. You don't have to get one with this fat end here, but that helps hold it in the chuck. If you buy a Dremel too, they won't give you different sized chucks and you can't adapt it. So if you put it, you won't be able to hold tiny drill bits without buying their separate accessories, which is also very frustrating and stupid and overpriced. This is a 1mm high-speed drill bit. 1 millimeter is usually a bit larger than what you really need. A lot of people go 0.8 millimeter for a final hole, especially because often the donuts are very fine when you print your own circuit boards. I don't know why, but people print really tiny little component donuts, and they rip and tear. You can push and take traces off the board just so that they can squeeze the parts in tight. But you can see that these donuts are huge and the parts are still squeezed in pretty tight. The reason I use a 1mm drill bit is because there's two reasons, and one of them, sorry while I put the camera down, is because most circuits will use a diode, and this lead won't go through a 0.8, I don't think, very easily or at all. If I use 1mm for the whole board, everything will be able to go through, but this will just squeeze through. And also it's just a bit nicer for putting your wires through, because by the time you strip the insulation off, when you're a beginner, I remember I used to have a problem a lot. I try and squeeze the wires and the hole was too small, and some strands would fray off to the side. I'd have to cut the strands off, and then I'd always be worrying, are they going to short to something, short out? So yeah, feel free to get whatever size drill bit you want, 0.5 millimeters, but if I can get away with this massive oversized one, it works really well with my own circuit board layouts. I've designed them my own way. All right, let's get cracking. So I've mounted, there, maybe you can see, I've mounted the phone to my head as a crappy little GoPro, but it should be a good image. I'm not sure what exactly you're going to be able to see, so if I get things out of the shot, I'm sorry. I'll try my best to crop it and explain later, but it's not going to be perfect. So here is your schematic. The PCB layout's the one we need, and we'd put here one PCB for you, one PCB for me. Now there's one I've missed some drilling a little bit. I'll make this the one for me, and I'll put yours aside. It's pre-drilled, ready to go. This thing hurts my head. So, and you'll see this layout you're looking at is from the top down. I'd call this the bottom of the board. It's a mirror image of this. Now there's no labeling, no silk screen or indication, so you just have to sort of visually match up and say, oh, that's a group of two, that's a group of two. You might make mistakes when you're good. You shouldn't. But I remember when I started, sometimes I'd accidentally put something in the wrong hole. I didn't count the amount of holes from one side very well or something, and you have to desolder, and desoldering's a pain. It's bad. So the first components I put in, I look for the low level stuff, and I find the lowest level closest to the board and work my way up. And the reason is, if I put in low level parts, low resistors and stuff, I put it upside down. I'm not sure where you can see, and everything will just push up by itself. Whereas if I had some capacitors that were out here and then I tried to put a resistor on, it could fall down a little bit and it doesn't look very neat. And this will keep it secured to the board and not have any chance that you could accidentally push it and wreck the traces, push the traces off. Because really, this copper is just bonded to the FR4 board. It's a glue. It's just glued on copper. It's very strong. As long as you don't stress it and you do everything correctly, it's perfect. But keep in mind, if you could push a component, you're just pushing against glue. So everything should be down. So all the resistors in this circuit, unfortunately, are upright to save space, and they're a pain to work with, but there's only a few. So, and the only low component is this 1 meg, and that is the 1 meg bias resistor. So I'll get him out. I'm using all metal film. I don't know if you can see, but here are my components. 1 meg metal film. It will color code as brown, black, black, yellow, brown in this instance. And it's here. Hopefully you can see it's going to go here. Bend the legs down. Mine, if I do that, they're set up in such a way they're not squeezed in and tight like other people's layouts. It'll just perfectly match up. Center it by eye. Make sure, do your things neat. Now, there's no backwards way of putting a resistor. You know, it's non-polarized. It's going to work exactly the same way if you flip it around. I do everything in such a way that I can read the color code left to right or top to bottom. So if someone's working on the circuit one day, they can read without flipping it in their head. And not that it matters, but again, it's something small you can do. Now, I forgot to turn my iron on. I'm going to turn that on. It's going to warm up. It will take about 10 seconds to warm up. I'm setting this to 360-ish for what I'm doing. And I'm just going to do one at this time, because it's the only low-level component. And then I usually work my way up. I might do a few, like 6 resistors or something at a time. I'm cleaning the tip because it hasn't been used for a bit. Now let's see if I can solder with a phone strapped to my head. And I'm just blowing as I do it so the fumes don't go in my face. The air conditioner's on in here too, so it's taking the wind actually. And when you cut the excess off, don't cut down so low that you're cutting into the solder level, but cut down low enough, as close as you can, because as you go around, if they're too high up, it'll prevent you from getting and cutting other components, and you'll get higher and higher as you go. Now hopefully you're getting this on the camera. So the next one up, the next level up in terms of height, is this little ceramic capacitor here, and that is this one. Normally, that's the radio frequency, high-end frequency you roll off. Depending on what value resistors before it, this is a very, very small value. It could be anything up to 220, but I don't want to influence the tone. 220 will be just on the edge of audio. So I'm just going to put in a tiny 100 would probably be okay. I'm going to put in a 56 so you can see. Hopefully you can see 56 picofarad, which is really nothing, but it's just a small nicety. It'll roll off, you know, radio frequencies that are out of audio. And I've just bent the leg so it's going to sit in position. Hopefully you can see that. I hope. And I'm just cleaning the iron again because I haven't used it. Assuming you know how to solder. I should probably not be telling you these things, sorry. I'm just going to straighten things as I go too. So everything's going to be symmetrical, nice. So this is the input here. And this will match the input here, the guitar signal. So sometimes when you're thinking about circuit boards, and especially if you're doing an ion-on transfer, you have to imagine things flipping. So this is really going to go in the box this way. So guitar in will go in through the circuit, out, and then out. But when you're looking at the other way, of course, you have to get used to thinking, well, now this is the input, that's the output. I remember when I started, I was trying to debug a circuit for hours and hours, and what happened, the true bypass worked, but the circuit didn't, because I plugged the in into the in, because it's always on the right, and the out into the out, but upside down. And again, this is upside down because it's going in this way. You know, maybe you've put your circuit board in that way. A lot of people would do it that way. So the in's flipped. Anyway. Next up, capacitors done. So the next level I'd say are these upright components. So 220 ohm. Now I'm going to put these aside for you too. So there's a 220 ohm. It is red, because red is two, red, black, brown. Reds, browns, orange, that you'll find black, they all look very, very similar. So one for you, one for me. There's yours, there's mine, and I'll get you a 1 meg resistor as well. One meg resistor for June. Do I need any more later? Yes, I will need one later. One for me later. One for June later. Normally I don't leave things lying around because you can forget what the value it is, and if you accidentally put in the wrong value, say at 1k really looks like a 10k and that really looks like 100k, I just do anything I can to minimize making a single mistake. So these are unfortunately upright, they're a bit of a pain. Still a simple circuit, and that's the 220 ohm here, 220 ohm here. It doesn't matter which way you do it. I've just got a system for the way I do it. And I'll probably do a few now. So yeah, like I said, there's a 1 meg ohm over here. And it'll just bend around easily. And you know, you're sort of matching up. I can see there's a group of two, big group of two, there's a tiny group of two at the top. You can count from the top to bottom off the edge. And the more components you put in, it's going to be more obvious which holes are for which component. Let's see, I'll chuck in a couple more. So, whoops, just hit my head. I might do some of these 10Ks. I've got 1, 2, 3 10Ks. So 1, 2, 3. And I would check them all with a meter as you go. Definitely do that. Check them with the meter. In regular production, I know it's in the right drawer, but I just look at the colors before I put it in to make sure that they're right as well. You shouldn't. I don't expect to have the wrong components in the wrong drawer, but You know, 1 in 1,000 is enough to be a problem. So there's a 10K. 10K here. And this 10K here is this one here. Now, it's not necessary to bend it like I do. It just means I can hold it upside down and it's going to be okay. And one last one. The other two 10Ks are these bias resistors. And they can be anything as long as they match, you know, 1K up to 1 meg really. Practically 1K, 10K to 100K practically. Now I've got a few extra components on, so that's enough. I'm going to start soldering again so I can cut them off and make more room. Any more than that, and I'm really having trouble getting into the corners, and I'm pushing down just lightly. It's sitting there on the board by itself on my desk. So I usually try and find all the ones I can access from one direction, turn it around, get them in the other direction. Oh, missed it. See, I can get this one here, but this one's on the wrong sort of side. I think that's the last one. Yeah, it looks like it. Cut these directly into the bin would be good if you've got one nearby. Here's my bin with some tea in it. Otherwise, do it in a pile cleanly. Yeah, that's pretty cool. You know what I forgot to do though? And I've squished some of these. I'll straighten them up now. It doesn't matter. It's just nicety, you know. It's not going to make the circuit sound any different which way they're facing. I completely forgot to drill out the holes for the switch, the foot switch. It needs to be 2 millimeters. I would probably progress my way up. This is a 1 mil hole. Get the one in between. I know this one's blunt though, so. I don't normally do this over the bin, but I'll get some light up here. I don't want to stab myself, obviously. Now this would have been much nicer to do before I put all the components in, but probably with a drill press, not by a hand drill. Alright, June, I'll do yours better. Luckily that copper's pretty good. If there's lots of burrs and stuff, if the drill bit's not very sharp, I'll probably grab like a double the size up and very gently deburr it. Or you could use a countersink tool or a deburring tool, even better. But you know, whatever you've got on hand. Yeah, I've made all this mess I don't want. So, what resistors are missing? The missing ones are, it says 1 meg here, but I'm going to put something else in there. That's done, that's done, that's done. The diode is missing, and 10K. That's all done. So, let's put the diode in. It's a 1N5819. That won't drop out as much voltage. These will drop out about 0.1 volt. A regular diode might be 0.7, 0.8, 0.6, depending on how much current you're drawing for a silicon diode. So I haven't labeled the polarity. This is polarity sensitive. It cannot go backwards. If you do the whole circle, it won't work. Now the positive is going to come in here, this is the positive end. The negative end is always marked with a little band. In this case, it's a white band, but either way, it's going to have a band of some sort. But what I want to do is use it. This is a retrofit. It wasn't on the original layout. I don't want to draw a new layout just to put it in. 47 ohm resistor. That's the filter one up here. One for you, one for me. I'll get you a diode as well. Now this is 47, should be yellow, purple, black, gold. And when you hit gold, you know it's in very, very low ohms. So the way I would do this, I'm going to draw it. Here I've got written to put in a diode. Originally I didn't use this resistor, and I've worked it in. So I just do on the board 2 components and I twist them together in the middle. So that will be in series, the diode and the resistor. So 47 ohm. Let's see, the way I've shown to do it, it doesn't matter, you could twist them. I'll twist this one around. Because one wire is much thinner, it's twisted pretty easily. It's hard to twist the diode wire, it's very hefty. As long as the diode's facing the right way. So again, the positive will come in here, which is here. So we need the positive end to touch the positive end of the diode, negative end, which is the lower voltage end. So if it's 9 volts coming in, it should be 8.9 volts-ish coming out with one of these diodes. But, you know, do whatever you want. You can get rid of this. I'm going to push that down as low as it will go now. And then solder the other side. Hope you can see. Sorry. So I've just soldered them together at the top. Cut it off at a reasonable spot. Doesn't look very neat. Yeah. Anyway. See, now I'm saying these other components are pushing up where I can cut this lead. So I can't cut this one very low because the other I have to take it from the other side. So it is good to get them as low as you can without compromising the solder joint. Hey cat, bye-bye, go away. Very nice to see you. So what's missing? Most things are in there. I need a FET. FET. I should have a container down here somewhere full of the FETs I need. I think these are it. No. Here we go. Nope, these are fake Chinese J201s. I've got 1,000 of them. So if you buy a J201 off eBay or something, they are very, very likely to be fake. What's this? Oh, so this is why you should label them. Which I do, but you know, it's just got so much stuff. Not here. Here they are. Oh, back in there. This is my OC 42s and stuff collection. These are 2N5459. There's a Fairchild, not fake. Like a 5457. I'm using a 5459. Better in this case, they'll make better buffers than J201s. One for you, one for me, as usual. You should do ESD, electrostatic discharge, with FETs, in theory. But it's going to be okay. Put it in the correct way, obviously. Now what I do, and then push it down too tight, try and get it straight and about where you want it. And just do one leg. This is the one I didn't drill very well. There we go. So it didn't matter in the end. And then straighten it up. So you've got a little bit of slack. But as soon as you do two legs on a component, it's really locked in. And you'd have to, there's no movement room. I've done the opposite side. And the middle one. Now, these guys are very sensitive. So if you're soldering 3 legs, you have to be very quick. If you muck around, there's a blob or something, come back to it, go do something else, come back to it. I guess that's a rule with everything, especially chips and transistors and stuff. Resistors are pretty tough, capacitors can be pretty tough, but semiconductors can be sensitive. So yeah, I'm running out of components that need to be put in here. That's what I didn't show you. There's one here that's labeled 1 meg, which used to be here. Discharge for the cap, but it doesn't really need it because the switch shorts out the capacitor, so it's got 0 ohm resistance. So what I'm using there is those 2 Zener diodes. 2 for you, 1, 2, 1, 2 for me. Now with these, like I said, it doesn't matter which way you put them in. It can be both that way, as long as it's either face to face or butt to butt. So anode, I've got 2 anodes on the same side, cathode same side. And again, this is going to be one where I'm going to twist them, put them in. So those 2 diodes will take the place of that 1 resistor. You could put in the 1 meg resistor if you want. Yeah, perfect. These are very nice legs, by the way, too. If you ever get nice component legs, you can save them aside in a small container like I do. If you get long, clean legs, good for jumpers and stuff like that. Not that my circuit boards use jumpers. I hate jumpers. I've done one end. Let's try and neat them up. Yeah, now it's flat on the board. I'll do the other side. Oh, camera slipping down off my forehead. So what am I missing? I haven't done these capacitors. I'll do them after I put the switch in. That's all done. I've put in a resistor here for the LED. You can't run an LED without a resistor. It burns out. Now, the different LEDs use different resistors. So there's a few sorts. You can get the high intensity. I've got one here. Clear LEDs. These are the brighter modern ones. They're much more expensive. And the way that they work, they're brighter because they mostly shoot out from like a 15-degree viewing angle, most of the light. So they're concentrated, that's why they're brighter, for the main part anyway. Because they're so much brighter, you use a larger value resistor, so less current will pass, and it won't let it become as bright. If you've got a simple, traditional resistor, like I've got these guys here I like using, one for you, one for me, off 9 volts, the maximum I would use for brightness, so the lowest value resistor would be about 1K. You can go lower, but at that point you're really starting to just make heat and not so much light. So you're within the ratings of the LED, but it's just a waste. These guys, I'm going to flatten out the leads so they can just come straight down. Anyway, so these are the ones we're using. I wouldn't use a 10K, they're not high brightness. I'll use or maybe a 2K. That way too, if someone decides to run this circuit off 18 volts, when voltage doubles, then current quadruples. So there's one I forgot that's missing. Sorry this video is so long, but it shows you what happens to build a guitar pedal. And I know this circuit pretty well, and it still takes me a while. This isn't soldering. So the one thing that's missing here, this big 220 microfarad cap, and like I said, that's overkill, oversized. One for you, one for me. I'm using a low ESR capacitor here, they're better for filtering in theory. But I didn't use a non-polarized small value one with it. So positive will obviously be up this end, negative will be up this end. And you can tell the negative because it's got a bar on one side. So there's your bar, just like diodes. I'll give you a tip too with the LEDs are a kind of diode, and there's 3 ways that I know of telling the polarity, which end's anode, which end's cathode. Now, woo, it jumps. The negative side, with components, if there's a negative side, the lead is always shorter. So this is the negative side, it's ever so slightly shorter than this side. Same thing with the capacitor, it's negative because it's marked, it's negative because it's shorter. Besides that, that's one way. The second way, there's a notch, don't know if you can see it, but there's a flattened edge on one side of the diode, the LED, the light emitting diode. The notch is the negative side. And the other way of telling, the way that I prefer, because it's guaranteed, I've even seen some that were mislabeled backwards, is inside the diode there is, it looks like a triangle and a very small little point. It's the same sort of way a point looks in a transistor. Now the large bit that's a triangle, it looks like an arrow sort of, points towards the positive side. So I look at the actual junction, and that's how I tell. Anyway, this needs to go in. Sorry to talk so much. I'm putting in flat, bending these sideways a tiny bit, and that's nice and rigid. The good thing is having a camera strapped to my head means I get a free torch as well. Quick soldering, and that's it. So the only things missing are those input-output caps, the foot switch, and all the wires. There should be 4 wires, in, out, positive, negative. Very simple. So where's my foot switch? I had him over here. Now normally I don't like when people do circuit boards mounted on a foot switch. I think that's kind of flimsy because you're putting a lot of weight. You know, if you drop a pedal, bam, all the way to the circuit board, if it comes out here, stresses. It's very difficult to change the switch. You have to desolder it, make a mess. It shouldn't. These switches are solder terminals. They're not PCB mount terminals, so they're not really made to do this. I'm just talking against myself and my design here, but to be fair, in my favor, it's a very, very tiny board. It's not going to put any weight. It hasn't got a wide counterbalanced weight or counterweight. All Also, the drill bit size I've used, you'll see at all lines, it's going to be an extremely tight squeeze. So I'm not relying on the solder to bond to the copper, and it's not relying on the traces to hold the board in place. I could drill this higher and I could slide it straight on, solder, but then you're relying on the copper and the glue. This will be a really, really, really tight squeeze. To do this, make sure it's all aligned without hurting yourself, please. And it's just starting to go in. Really be careful not to bend the leads. Oh, it's going now. If you're missing and the leads, the lugs are bending, then oh, that's bad. Not normally this tight, it's just because somebody's watching me do it. But you can see it is extremely tight. That's the way I want. I want it mechanically securing itself, not secured on by solder. There we go. And now I just visually make sure it's all aligning, it looks level, because if you do it lobbed, it's going to touch the enclosure. Anyway, it's pretty good, pretty good. And see, that's extremely firmly rigid. It's nothing to do with the solder, nothing to do with the copper. That's going to stay there very well. Now, these switches, these are the very, very good CIC brand switches, Taiwanese origin, and these are the original ones that go way back. There are many copies and models. I should get another one to show you. I've got a bag of them here. I get these from Small Bear Electronics, and he assures the source is reliable, straight from the manufacturer. There's no interceptions, because there are cheaper switches. They work and people use them even in production, boutique manufacturers. But these, I guarantee you, these are better. I have used different brands before for personal things, and they are flimsier. The epoxy isn't as good. They can click and pop, and the contact isn't as quick and neat and strong, and also that they come back. They fail. You know, there's only so many times you can click these, and this one has 10 less now. But you know, I don't want a pedal to come back in 2 years, 6 months, 4 years. At the moment, I've got a 5-year warranty on mine, and I don't get things coming back very often because of, ironically, the ones that have come back. I think I got one back from June, and that was the last 500 switches that have lasted before that without one failure. So that's, you know, 0.2% failure rate so far. But my point I want to get to is these can't take very much heat. You have to be very quick and very neat on the soldering. And the way we're doing this is horrible because you're applying lots of heat, lots of solder. Luckily, it's securing the lugs, so they don't really get an opportunity to wobble, wiggle. You find if you heat it up, you could bend the metal, which means if that's bending, it might be making bad contact inside too. But I'm saying, please be quick, be neat. If you've taken too long, put it aside, do something else, come back and solder the rest. So let's get started. And this is where leaded solder might be better. Or even I might turn up the iron temperature here. It sounds counterintuitive, like heat damages it, but if I've got a higher iron temperature, I can get in and out quicker. As like wattage, it's the overall value of energy you've put into this. So clean my iron, and this is tricky, but I sort of feed it from one side, then I move the iron over the other side to. Now, because the solder has flux in it, that guides the metal to heat. So it could be bad. It's guiding it. The hottest thing in this equation is my iron, so it's guiding it to the iron as well. But if I take it from one side and then sort of move it across, you see the heat from the iron sucks it to the other side of the switch. I need just the right amount. This is too much because it's gone off to the edge, but that's okay. So yeah, that's very, very hot, untouchably hot. I would probably go off and do something else. Especially if I'm going left to right, I'm going to do the same thing, which that was left to right. I'm going to go left to right. So as I'm going, that's had time to cool, that's had time to cool. Same thing if you're soldering ICs, chips, op amps. If you have to make any little corrections like I just did, it's better to do it now while it's hot. Strike while the iron's hot. But if you've stuffed around for 5 seconds or something, that's too long. Pull away. And a good sign of a good joint is that it's really shiny. If the joint is dull and it looks matte and it's not like a mirror, it's not like chrome, then it hasn't solidified very well. Things that could cause that, you might have imperfections on, you didn't clean up the copper very well, or the biggest thing is that it's been moving, it hasn't been at rest when it's solidified, when it's cooled down. So if I was agitating it, it might be a problem. Leaded solder, everyone says that they have duller joints with unleaded solder. I find if you use it better, you'll get a shinier joint. I mean, look at this. Leaded solder won't look like that. Especially not down the track. This will stay like this for a long time. Leaded solder ages and it oxidizes a lot more. And so will this. This tinned circuit board will oxidize, but still everything's protected. That's done. So switch for you, my friend. Some of these 1 microfarad capacitors. You'll need 2 in and out. I'll need 2. Oops, I just dropped one. If you didn't have them, you could use a 10 mic or a 22 mic electrolytic. And the reason I've put these in last is because I wasn't sure of the size and how much the switch might push it out. And it looks like it's perfect, but that's okay. Look at that. There. And I'm soldering from the edge, not the middle of this big copper trace. Wash your hands when you've been touching solder. This is lead free, but especially a leaded one, you get lead poisoning. You know, it's in your hands. You get to eat. It's on your food, in your system. Yeah, don't go have a sandwich or something for lunch without washing your hands pretty well. Glad I remembered to tell you that. Oh, no, I forgot this 10 microfarad electrolytic. And you're probably thinking that before, like, why didn't you put in the electrolytic? He's not doing it. He's not doing it. That 10 microfarad is this 10 microfarad. It's for it filters out ripple in the bias section. And the way this is done, it's made a nice stable, clean voltage and injected through a large resistor. That's called noiseless biasing, as opposed to 2 resistors going straight onto the signal, making a bit of noise. Anyway, 1 for you, 1 for me. And sometimes you see that instead of going to another voltage, you'll have 1 meg. It's a positive and 1 meg to negative, and still in the middle you'll get half the voltage. An alternative to that, sometimes you just see 1 meg to ground. Now I'm actually put this in correctly. These will be damaged if you put them in backwards. Now the spacing wasn't perfect on this, but if you push it hard, it'll go to the side pretty well spot on, and it'll be upright. And then that will be it. The only holes left are ready for wires. I think we can take a break, move on to the enclosure, and then we'll come back, do the wires, and then drop it in, and that'll be it. That'll be done. One circuit board. So, here's my box, the enclosure. This is a Hammond 1590A. It's an official Hammond brand. If you ever get a 1590A open quotation enclosure, it's usually not this brand. This is the original brand, and people have modeled off this enclosure. These are very, very, very nice grade of aluminium. Very good to drill. Very heavy. It's a much better brand. It's the best brand. DC socket. One for you, one for me. Now, this is a 2.1 millimeter barrel socket for a barrel, a 2.1 millimeter barrel, which I have here. Dropping my wire. It must be a plastic kind. You can get these in metal, but it must be plastic because on the outside of the power supply is positive, and on the casing this will be connected to negative. So if you had it metal, as soon as you touch that, the positive would hit the case and short out, and it's a power problem. The reason they are this way is because Boss Ibanez has been using this configuration since the 70s, forever, because that matched the sockets that they had that we have now. It means that it can switch properly, and so yeah, you get this big ugly plastic thing, but that's the standard. So make sure you get the plastic one, don't get a metal one, that's my point. The other thing is, this is a 13 millimeter drill hole. There are cheap Chinese ones that take a 12.5 millimeter drill hole. Much cheaper, but they are flimsy, they are nasty, crappy. I've used them before and they're not worthwhile using for me. They work, you can feel the connectivity in them isn't very good. This one I've got here, I believe, is Taiwanese. A lot of good stuff comes from Taiwan. Yeah, it's not as good as Japan, for example, but I'd always take Taiwan over China. China can be fantastic, it can be perfect and great, like Apple products, but you never know too. There's no export standard. Now this is why I've got these. This is very, very tricky. This will probably be the hardest bit. You'll notice I can't really get a shifter in there, no matter which way I do it. It's going to hit the bottom, it's going to hit the sides. I can't get a socket in there because the socket will hit these. So the only way I can do it, this is very hard, please don't hurt yourself, is with some pliers. Now I'm doing it, I want it to be upright like this by the time I finish. Now if you slip doing this, I've done this before with pliers, if you ever slip with pliers and your finger's in the middle like I have now, you could get caught in here, it will bleed for a very, very long time. So please don't hurt yourself. Don't copy me exactly. And I'm just trying to tighten it very practically. That's about as tight as I can get that without me hurting myself, without scratching all the enclosure down. It's just a very crappy setup. There's nothing you can do. This is the way it has to be done. And that's about as tight as I can get that. Now if I want to go a tiny, tiny bit tighter, there. And because I've gone the opposing way to the nut, it's tightened it even more. You can still undo that if you had to one day. DC is on. Furthermore, the hardware I need, a couple of mono sockets, two of, one for you, one for me. These are yours. These are Switchcraft branded. These for me are the best sockets. They're the most expensive, but you know, that's the way I like it. I've also got some star washers, lock washers, whatever you want to call them, serrated washers. And what that's going to do is help ensure that the metal sleeve of the socket and of your audio signal will make a perfect contact into the chassis aluminium enclosure onto earth. Because obviously resistance in your signal is bad. You don't want a crappy signal or a dodgy connection, especially if this oxidizes in 20 years. You don't want to sort of be a little bit rough. If there's your guitar signal off the tip, say for example, this is the audio signal, you don't want a crappy connection, but the earth is equally as important. Without the earth, it's the opposing, it's like yin and yang. One's not going to make sense without the other. They're relative to each other. So, I think we can do this now. I'm going to put these on. I use a socket, but you can use a shifter. Now I've put this in such a way so that it's bending with the smallest inner wall to the jack socket, the socket, because that's the smallest part in the, well, I hope that makes sense anyway. And again, this washer, they're a little bit imperfect from the factory, so I do it in such a way that it's going to squish down and look flush and not be concave coming outwards. Not that it matters. Usually there's a dressier side to a nut. These are equal each side. So if you use a shifter, I do it that way. If you do it that way, there's every chance you could slip. You very well might. You'll scratch the powder coating. Same thing. You could slip doing it this way, but there's much less chance. But if I use this, there's nearly no chance. And that's so tight. And because of the star washer, that will definitely stay tight for the rest of the life of this pedal. And I'm assured that is a good connection. It's as good as a solder joint, maybe better. Same thing. Normally use a mono and a stereo for power switching, but because there's no battery, this is less soldering. It's going to be redundant to use a stereo input. And I'm just putting in an opposing strength here so it doesn't twist as I tighten it. And that's the hardware mounted. So the only step now will be the wires and dropping the circuit board in, turning it on. Okay. Now for the next segment, just doing the wires. I'll turn my soldering iron back on. Always remember, oh, hit my head again. Turn the soldering iron off when you walk away so you don't wreck the tip and I guess waste power. So I've done everything in two. We're going to color code everything. So the red wire is positive because red's positive. It's fairly obvious. So that's a red wire. There's in and out. I'll make them blue, and they're both the same length. In and out. And the negative on the board is here. I'll just do it as black because negative's black. Cool. So the way I do this, I use a razor blade to just strip the wires. And there's one more, wire that's a brown one. It says in, out, positive, negative, four on the board, and there's one later to join the negative enclosure to the power supply DC socket. So it's pretty simple. I just visualize as I'm going how much wire I need to strip. So I need about that much, this is positive, to go on to, grab a sharp blade. that much to go into the DC socket, and what's that, like 2mm to go onto the PCB end. So they're about the same each end, 2mm. So that's the DC positive. These are the signal in and out. So I need to get again about 2mm on the PCB, and to the jacks I need 10mm. Now there's a little bit, 10mm is about the largest amount of insulation I ever need to strip. So you get this little sleeve. I like to use that for transistors and stuff. And we'll use it later for the LED. So it's good to recycle what you can. You don't want to waste, throw everything into the landfill. So again, I'm just visualizing the length I need, where the wire is going to be going. And I'll keep those little insulations, the 10mm, as quick as I can, without hurting myself, obviously. Now this one is going from the board, the PCB. I always do the smallest one first, because you can always cut it longer later. And the other end, I need about 6mm into the jack, not 10. I know this because I've made a lot of them. And let's see, this one is going to go from, sorry, I shouldn't call it a jack, I should call it a socket. The DC socket into the earth of the audio jack. It's the input. And again, that's 10mm, so I can save those little 10mm spaces, are pretty useful. Now I've got these wires, I'm going to pre-tin them. You could use a solder bath, but it's just a few wires. I'm not going to bother warming that bath up. And the best way, if you find if you're pre-tinning a lot of wires, you can quickly blob up a lot of solder on the tip. The problem is it blobs up because there's no flux. Give it a tap. The best way to not waste a lot of solder and have to clean your iron all the time, remember the solder is flowing in the direction of the heat. So I heat up the wire and then let the solder, I touch the solder at another point of the wire so that it follows the heat. That way I'm not pasting it onto the wire. I'm not trying to smear it on. I'm letting the heat pull the solder, and I'm using as little as possible. We'll see how many I can do without having to clean the tip. You could do a few at once, like I could pick up 2. This is almost all of them. I'm getting a little bit of a blob of solder on the tip now. Now be careful if you're tinning really long ones like this. If you hold it here and tin it, you could make a catapult, and it happens to me a lot. You know, you do this, and you push back, and it flicks right at your eyeball. So tinning wire, try not to push, don't flick. You might get solder in your eye, which is horrible. And that's it. I went through all of them. None of these positive ones I haven't done. It's positive I did. I wasn't really. I was hoping it was going to start blobbing up so I could show you when you need to clean the iron. But yeah, the iron's got a bit of a blob on the end of it. If you find some of them aren't rough and smooth, there's a blob. That's the last one you do. Add a little bit more solder, because when you add a little bit more solder, it will add new flux. Get rid of the blob, flick it off, clean the iron. You know, I usually don't clean my iron before I put it back. I let the solder stay there, protect it, and I clean it before I use it. And these are the wires. So I'm going to get started punching them in. I'll start with the shortest one first. That's okay. Now, you don't have to tin the end that goes to the PCB. Depends what sort of wire you use. If you think all the strands are going to split up, then yeah. If not, you could tin it when it's done all in one shot with the PCB holding the wires. I'll say this positive one's the second longest one. I've got to be careful, where's that going? Here. As always, I'm just blowing as I do it. In and out. Should be the same length, I believe. So this one, for example, I didn't tin very well. I probably shouldn't have. That's okay. If I really want to start again, that's good now, but use a bit more solder. The new flux will shape it up with a clean tip. Yeah, there we go. And again, this wouldn't have worked so well if I didn't use a 1mm hole drill bit. Just depends what the circuit board will accommodate. And that's it. The only two holes now remaining are for the LED. Now for that, I'm going to recycle these sleeves. Probably try and find the longest ones. Well, you can have the blue ones. I'll have these brown ones. They're both 10mm. I'm going to put it on the positive side, because that's the side I probably least want to short out. You know, if the negative shorts to the earth, it's negative shorting to negative. It just means the LED will come on. Big whoop. I believe this is how I do it. So yeah, that should work. Now you have to do this the right way. Positive will go to, well, the positive side obviously goes to where the positive is. The negative is what's switched through the switch. So positive, the one I've just put the sleeves on, will go on the left. And push it down. Bend the legs out a little bit. And again, I'm just going to solder one side, then straighten it up, make sure it's okay at least. Try and center it. That's pretty good. It's all the way down, yes. And do the other side. If you soldered both, you couldn't really bend them. If you try and bend it after you solder them, you're going to stress the copper joints at the bottom. One circuit board done. Now these are for you. That's for you. That's for you. There's one wire that we have to put in the enclosure, and that's going to go from the negative. That's going to attach the earth, the chassis, to the negative on the DC socket. So it's going to go from here. I'm going to make a mechanical bend. So just past halfway, make a little hook, feed it through, bend it round, then bend it roughly where I want to go. It's much better if you bend it at least in the direction that you want before you solder. I'm not going to solder this yet because there'll be one more going on later. There's two wires that go on this connection, but I can solder this end. I probably won't be able to show you on the video, but you don't need to see. I'm going to get it where I want it first, if it's possible. Otherwise, if you try and move it now, this is incredibly vulnerable and weak now. Now that you've soldered it, it's brittle. It shouldn't be, but it's much weaker than it was as just being a wire. You could bend it as a wire, but now it's, instead of strand, it's a big soldered, solid thing. So it won't break strands or just snap. So you can probably, as a good rule, I'd say you can bend that about 3 times if you have to. Anything more than that, you're pushing your luck production-wise. I wouldn't sell that to somebody. I'd reflow it or do something to make sure I know it's going to be okay. Or if I ever do need to move a wire around, I'll just, I'll reflow it again at the edges when I know it's in its last position, and it's good. Now these wires, pull them off to the side, they're the ins and the outs. The positive will come up and connect to the positive on the DC socket. And this black one for the negative, it's going to connect here where this other negative is for the brown one. I'm going to put a hook on it now just to make my life easier. Unscrew this. No, I'm not going to use these. I've got the extra fat version nut. Now the job here is to align this nut height so that the LED should just start poking in past through the enclosure. So I can see like that's where the enclosure level is going to be. So it might be a bit of trial and error, see what this looks like. And hopefully that LED should match up. If it doesn't, you might need to bend it a tiny bit or something. And that's pretty good. Now I'm more happy with the LED matching than the board being wonky. So that's fine. These will shift it very, very, very carefully so that I don't scratch the powder coat finish. And as I'm tightening it, I'm making sure the board's not shifting with it. And about there, looks like it's level, looks neat. And there's 4 wires to hook up, and we're done. Okay, I'm back. I couldn't finish up last night. There's only 2 minutes left. But it's daytime now. We've got some light and nice and sunny outside. So there's 4 wires left: input, output, positive, negative, and that will be it. We're on the home stretch. So get the input wire through. And then make a nice mechanical joint so that it should bend back, not all the way, just leave a little bit of uninsulated wire left so that the solder doesn't go right up to the insulation. That's about as tight as I'd like that. And get the wire where you want it before you solder it, so you're not going to stress it later. Just turn my iron on. And use the heat to transfer the solder where you want it. That's about as neat as that's going to get. It's a real minimum just to fill the hole. So that's input. The other blue wire was output. The good thing is with these jacks, if you don't know which is which, you can visually follow them really easily. This is obviously the tip that carries the audio, and just follow the metal that comes along this layer, and that's going to be the audio tip. Same with the stereo one. If you follow this layer, this lug, it goes straight to the sleeve, so that's going to go to the enclosure. It's pretty obvious. That's why I like these ones too. Let's see. Fold this one over. If you don't want to do this, just plug it in, solder it up. It's the same thing, and cut off the excess wire. Again, I'm using the heat to guide the solder where I want it, and that's about perfect. I'm not using this terminal because I've used the star washers, so the earths are already joined through the enclosure. Now this is the black one for the negative that I put a hook on before, and you'll see why. Not necessary, but I just knew this was coming. the most fiddly wire to do. Bend it the way I want it. And get it coming from the angle I want it to. There we go, I think. Push it in, yep. And then crimp it down. Perfect, look at that. Now, the earth terminals are the hardest one to solder because this earth lug, negative, the metal comes and it touches the enclosure. So it makes a giant heat sink. So if you don't, you might have to let your iron be as warm as possible. Otherwise the solder might just blob on and paste on and not take to the metal. This is a 100-watt iron, so I won't have a problem, but if you had a lower wattage, like 20 watt, even I think I had a 40 watt or something, that these were a problem to solder because you need to dump a lot of heat, so that heat heats up this lug before it gets a chance to just disperse through the whole enclosure. Last wire. This is the positive. I'm going to get it out from amongst all these jacks. Go over the top of the jacks, because don't forget the audio jacks are going to come in here later. I don't want to hit this wire. That shouldn't be a problem. And so I'm just going to raise this up so that the jacks can come in. Yeah, it's missed it by miles. So that should work. And there's the LED. Plug it in. Oh, really, double check all your soldering. Make sure there's no gap, bridges. There's no dry joints. I pretty much do it as I go, so I don't check at the end, but really you should check. Make sure there's no little tiny blobs or even better, sometimes you need to clean up. If there's any little bits of flux or wire, there's a little bit there. You know, flick off any blobs of solder off the board with a little pick or a screwdriver or something, but this is all very good. So cool, thanks for watching, guys. So you can see that probably took a couple hours or something to watch this whole video, but on top of that, the enclosure, powder coating this outside in the garage, drilling down the boxes, making the circuit board, acid etching it in an acid bath. This is only $99 AU Australian, but you can see that it's taken hours and hours and hours and hours, and the parts is a large part of that. Most of my pedals are about $50 in parts. This one's less because it hasn't got controls and it's very minimal, but just something to consider. If you want to build pedals to save money, it might not always work. Depends how you do it, and if you want to spend a lot of money. I said parts for my pedals can be $50 Australian, but it's possible to do it cheaper if you get all the very, very, very cheapest stuff, maybe 20 bucks. So if you've got a weekend and $20, you might be able to build a pedal. Just depends the quality that you source, and it'll sound the same. It'll work. Cool. All right. Thank you.